your presentation. Thank you.
Well, thank you very much, Claudia, for the kind introduction. I've heard that there are a lot of young engineers, students in the audience. So I may shift the traditional view a little bit, if I might. So first of all, some preliminaries. These slides, they contain some links and URLs. You can get them if you go to simplex.com/FeenoX. Then you will get a link to download the slides. Then you can see also the samples and all the figures in a GitHub account down here. So I'm going to briefly speak about nuclear-related computational codes, following Simon Sinek's first why, then how, and finally what. It's not the other way around. So if you haven't seen this video, it's a TED Talk, I urge you to. So just follow this link and watch this presentation. So let's start with why. This is a pretty common and very old benchmark from the International Atomic Energy Agency back from the 70s. It's an electronic benchmark for PWRs. And you can see that everything is like essentially square because fuel elements in PWRs are square. So it's reasonable that most nuclear codes use structured grids, square grids. Now, let me tell you a story. What happens in Argentina, please? So we have heavy water reactors. So that means a natural uranium. And since we don't have way too much reactivity, we need a refueling machine. So the refueling is done daily, on a daily basis. So we have to make room here up. We have to clean up this space above the reactor to make room for the refueling machine. So that means that the control rod has to go slanted into the core. So not only we have slanted control rod, we have cylindrical channels because the moderator is kept at a different temperature. So we have separated moderator from the coolant. So we have circular fuel elements. So if you start to use structured grids like cubes to model circular fuel elements, okay, it's like playing Legos, with the slanted control rod, it's like playing Legos. At the end of the day, it works pretty well. So you can have like individual coolant channels with different burnups. And for fuel management, that works more or less okay. But then what happens on transient cases? For instance, so let's consider the emergency boron injection system, the second shutdown. So we have nozzles that go slanted into the core, and they release a solution which is rich in boron to absorb the extra neutron and shut the reactor down. So now you have slanted nozzles that insert very quickly a boron solution forming a plume. So they go inside in the middle of these coolant channels. So now playing Legos is not as cool as it looks. So you have the nozzles here, like modeled with cubes. So you have the plume, and this is a transient case, very fast. In less than 1 second, you have a plume developing. And then when you want to do transient neutronics, so it's not that cool. What happens here? So you have your fuel elements, and you have a tiny drop of boron with a big concentration of boron. So if you have like a big cell, you end up with the whole cell contaminated with boron. So instead of 2000 ppm, you have one single cell with 100 ppm. So the drop that should be here is like numerically spread all over the cell. Of course, you can refine the cell, but still you have some problems. And at the end of the day, you are inserting numerically, again, boron inside the fuel element, where physically there's no boron there. So this is the why I started doing what I did. Let's switch to how. Before telling you how, let me tell you a little bit of history. So when I was in college, I had to solve like these equations for dynamical systems. So I had to either use a numerical method, program from scratch, use a numerical library, C Python at that time, probably today would be C++ or Rust, or use Octave Maxima or something worse, which is a non-free program which is called MATLAB. And I think it was like back in 2006, I didn't know how to even spell MATLAB because I was trying to use it and I was type in math lab, like mathematical. I was told that it was math because of matrix. So I was in college in this class of reactor physics, and the teacher says, okay, open MATLAB. And then I saw like a very big screen with a lot of squares and blocks and lines connecting them. And I asked, what's this? And he told me, oh, those are the point reactor equations to solve the transients. And I said, no, point reactor equations are these. And in any case, if I wanted to write these equations into a computer, I would do it like this. I would just write the equation down in a file and ask the computer to solve it. I don't want to put a block and connect it with a line to solve an equation. And then that was in college. After college, I went to work in the nuclear industry and the completion here in Argentina of the Tucha power plant. And what I saw was essentially this. So the state of the art, at least back in 2008, was Fortran codes. Fortran 77 mainly, and then were some cases where they said modern or advanced, they meant Fortran 19. And I can tell you, even now, that Fortran 19 is not advanced, so it doesn't mean advanced nor modern. Let's go back to the how. So we have a domain, and we want to solve a partial differential equation in it, in particular the neutron transport or diffusion equations. So the traditional way to go is put a structure grid over it, discretize it, so you have this so-called staircase effect. And instead of doing this, I said, why don't we do this way and use unstructured grids? Fair enough. So I started working on these two codes with Sora Milonga and Claudia. You directed a PhD thesis using Milonga to be coupled with other CFD codes. It was pretty cool work, and there were a bunch of papers related to that work. And these are some papers. If you just copy and paste the title, for sure, for most of these, you will get the actual PDF or whatever. So they are like published in open source or open access journals. So there has been some work with this improved version of the code that I started in college. And then I'm working on this version 3, like a third system effect that you can go into simplex.com/FeenoX. And it's like, I started the other way around. I started writing everything from scratch, but starting from the software requirement specifications, which is something common in the software industry. So what we want? We want some industrial level code. We want it to be extensible, and this is the key. It has to be cloud first, not even cloud friendly. It has to be cloud first. It's like if you want to design a web page today, you have to make it mobile first, not even mobile friendly. You have to start with mobile first, and then if you want to solve a problem nowadays, it has to be cloud first. So at the end of the day, you want to run it in the cloud with hundreds of cores and eventually infinite capacity. So the code has to be cloud first, and it should be scalable, flexible, and a lot of stuff. So the software design specification is the document that addresses how FeenoX, which is the code, tries to address each of the requirements, if you allow me. So essentially, it's open source, so it's about freedom, not price. Of course, it runs on Linux and not in Windows, because essentially cloud runs on Linux. Let's see a little bit in the following drawings what we can do with FeenoX. So we went through the why, how, and what. So FeenoX is a general code in the sense that it can solve generic differential equations, ordinary differential equations, for instance, Lorentz system, mechanical, heat transfer, or even you can solve a maze. There's an example of how to solve a maze using the Laplace operator. But in particular, let's say we want to solve point kinetics, which is what I wanted to do back in 2006. So we have our equations, and we have, say, a table and a reactivity table versus time. So we create an input file. So essentially, we say which are the steady state initial conditions, which are the equations that we want to solve. We give a table. So it's like this table is here, the equations are here, some settings about the end time and that stuff. So we run this on the cloud and we get our answer, of course, in a matter of fractions of seconds. So it's time adaptive. So you can see how the flux or the power in this simple case behaves versus the reactivity. And now we might want to do inverse kinetics. So starting from the power or the flux level, we might want to recover the reactivity. Okay, we can write this equation, which is the integral version of the reactimeter. You can find this in most nuclear reactor textbooks. Or you can solve an inverse problem. Instead of fixing the reactivity, we fix the flux and then we compute the reactivity. And if we just fit the flux level, then we can recover with either method the reactivity, for instance. We can solve the PWR benchmark, the one that we started with. So you, in this case, you say that you have an electron diffusion problem and two groups. You have the macroscopic cross-section. The cross-section can depend on space and take expressions into account. And then you get the result like the fast and the thermal flux, like very, very quickly. And you have the effective multiplication factor. And the thing with the unstructured case here is, yes, you can use unstructured. It doesn't make much sense to use unstructured grids to solve this problem, which looks very square. But then the problem actually has 1/8 of a symmetry. So if you use unstructured grids, you can exploit that symmetry, which you wouldn't be able to if you use structured grids. Then we can solve something like this. Okay, well, what's the flux distribution inside the reactor with the shape of a bunny? Okay, this is like S2 method, like neutron transport in 3D. And we can solve this because we can handle unstructured grids. And in this case, just to finish, let's say we have an homogeneous reactor with the shape of a cube. We know how to compute the effective multiplication factor there using diffusion. We know how to compute the effective multiplication factor of a sphere, and we know that it's larger than the cube. But for instance, a very valid question, what happens in the middle? When we go from the cube down to the sphere, okay, you can compute that pretty much easily with FeenoX because it can handle unstructured grids. It is cloud friendly, so that means that it's script friendly. So you can write a script and run as many simulations as you want in the middle, creating all the intermediate steps. So this is something that you cannot do, for instance, with a code that doesn't handle unstructured grids. You could do it with a code that is not cloud friendly or cloud first or script friendly, but it will take you a long time to compute all these dots. In this case, if you want to double the number of cases, you just change one single line, then you rerun and you plot. So the conclusions, and if these young generations want to have something to remember of this talk, is like in the 21st century, we have to talk about cloud first approach. So this is like the cartoon there. So what are clouds made of? Linux servers mostly. It's a good advice to try to stick to free and open source software as much as possible. This is regarding verification, validation, third-party review, and that stuff. And we have a lot of things to do with FeenoX, so we need more formulations. So Milong already had them, the previous version, but since FeenoX is a brand new rewrite, we are still missing some formulations. We have to work on this massive parallelization and on the documentation, of course. And a nice to have is to build a community, to have a forum, to have people to use it, to have people to ask questions. And if you allow me, I want to end with a message. This video, it's a message that I've learned a little bit. You can see it on YouTube. So when you go to college, this is what we are all taught about pendulums, formulations, equations, and that stuff. But then when you go to the real life, this is what they actually look like. And if you pay attention, the period does depend on the mass of the ball. So that's what I had to say. And maybe we can leave, Claudia, the questions for later.
Okay. Okay, thank you. Thank you very much for the interesting presentation.